Hello everyone. Hi. Uh, so recently I just started implementing machine learning algorithms from the basic statistical algorithms from scratch. I don't want to use any uh, ready-made libraries to use those algorithms. So I've been working in machine learning for quite a while, and I've used most of these algorithms. But most of the time it has been using some of the other library like sklearn, TensorFlow, PyTorch, etc. etc. But I've got some time to. I did have some free time, so I thought let me just uh, strengthen my fundamentals and implement these algorithms from scratch. So I started with a linear regression. I found a simple challenge in Kaggle. So this was the last month's playground challenge series that goes on in the Kaggle these days. I picked up this particular challenge, and luckily, when I thought of starting this work, this was the uh, ongoing competition, and it turns out to be a regression problem. So I just thought I'll go through it, implement all parts of till the building of the model, and then make a video explaining my work. Just see how is the video coming right now. All right. Okay, so this problem statement is basically a regression problem wherein the data you have is uh, pretty straightforward data. So let me open a file for you. The training file looks like this. It has, I think, 9 columns, out of which one is the predicting predictable variable or dependent variable, which is calories. Another is IDs, which is the unique IDs for each of the workout sessions that is recorded here. So basically, based on these features, sex, age, height, weight, duration, heart rate, body temperature, we have to predict calories, how much calories would have been burned in that particular workout. So uh, all of the except sex here, all of the variables features are numeric, and sex also obviously when we'll have to process it, we'll turn it into a boolean variable 0 or 1. So it is a pretty straightforward problem, as in uh, let me go through the notebook. So I also posted a blog post for this wherein I did the entire work of loading the data, understanding the data, plotting each variables, etc., and then understanding correlations, transforming variables, doing some pre-processing, then implementing the linear regression models from scratch. So I'll just this video is to basically quickly walk through this entire blog post, maybe in 5-10 minutes, so that uh, the main step that I want to get to is of implementing, showing you how to implement tree-based methods from scratch. We'll see why I need to talk about tree-based methods, but this regression problems have some shortcomings. So, which particularly suited in this kind of problem in this kind of competition. So I want to get to that point. because linear regression was one thing I never implemented from scratch myself. Mostly I use the sklearn or XGBoost kind of libraries to implement it. But this time I got a chance and I did some mathematics myself and then tried to implement those. So I want to explain it on the video here so that I can understand it myself again better. So let's go through this blog post quickly. We load the data, all the train DF test and original DF files. So basically in this competition, what they do is they take old competition data, they train a model uh, on predicting these particular problem statement, and then they generate some data out of it. So the training and test data that they provide in this playground series is the synthetic data generated by the models trained on this original data. We have all of these to train a model, and we need to make our predictions for submissions on this test.csv file. So as you will see, uh, there are as I already told you, there are 1, 2, 3, 4, 5, 6, 7 independent variables, and the dependent variable is calories, which I don't know why I printed the train test here. I should have printed train data frame, but okay. While reading the data, I use index call equals to id so that there's no there's no externally added indexes being done by the pandas library. So it just uses the ID column in our dataset in our CSV file to show it in the indexes. Okay, so we see there are no none values or null values. All the values are available. There is no missing value in our data. So we are sorted in that way. You don't have to worry about it. Then if you see, if you look at the, I try to print the statistics of all the features of the data here. So if you see train DF, test DF, I printed this upper one is train data frame statistics. This is test. So if you see, so I might not go through it in detail, but I'll show it here. The mean standard deviance, all the quartiles, min max, everything. If you match uh, corresponding features from train and test, you will see that most of the statistics are very similar. So we are safe in a way that we don't have to worry about thinking that okay, the train data is it from some different distribution as compared to the test. They look almost similar, so we don't have to worry about it. We can just train our models on the train dataset, and we can make the prediction on test. So distribution shouldn't be a big factor as far as I understand. We segregate the numerical columns and categorical columns from here. Wherever the called .d type train df column, this series d type is object, it will be a numerical column. It is not an object, it will be a numerical column, and where it is an object, it will be a categorical column. So obviously it will come out as all these height till calories, these will be numerical columns. Age would be the only categorical columns here. So I want to do some univariate analysis. First we try to plot the categorical column. So we have only one categorical column. Let me zoom in a bit. Okay, so we do the box plot and the pie chart. So from pie chart you can see that in the I think we are plotting train data. So it is well balanced throughout the data, and the male has calories distributed like this. So they have min max values quite similar. Their medians other quartiles are similar, but the male has quite a few maybe outliers as compared to female. Uh, yeah, otherwise it's okay, nothing to worry about. You see how the skews are working here, which of the features are skewed. So you'll notice that basically if the closer the values of this is to the zero, the less skewed it is. If it goes above zero and increases, then it is basically, we call it as right skewed. And we'll see in the plots individual of the individual features ahead. And if it is going towards the negative side of the zero, increasing in the magnitude, it is getting heavily skewed on the left. That's what we say. So we plot the numerical features here, each of those. Each numerical features we plot three different ways: hist plot, violin plot, and box plot. So basically, box plot is easy to understand, easy to find out if there are outliers in that particular feature. His plot or violin plot can give us a clear idea of how the distribution looks like. Is it a normal distribution or a skewed distribution? Those kind of things. So from here you see we plot age against count. So we plot the histogram of age. Histogram looks to be right skewed, and from here also we can see it is slightly right skewed, as in you see get the peak very much early on, and then you get values till 80. So the peak is around somewhere between 20, 22 maybe, and then peak goes on here. For height, it is well uniformly normally distributed. So you can see that there are quite a few of the outliers. In violin plot, you can see that this box chart here extends out of the distribution, this area. So there are a few outliers here, but it is good enough normally distributed, with the peak is spread for a bit of height range. Minimal skew, symmetrical, bell-shaped, approximately Gaussian distribution, we can say. This age is heavily skewed to the right, which also is visible from the number 0.4 is the skew for this. This suggests that mostly younger people using the workout monitoring app. Similarly, so I have plotted these histograms and box plots for all of these. Like for weight, it is a weird kind of distribution. Slightly right skewed. If you look at the numbers, it is slightly right skewed, but there are also a few outliers here. Similarly, if you see duration, it is a kind of uniform distributed variable we see. So you see equal count of workouts happening for each duration values. So that's a pretty straightforward value feature for us. Heart rate, we see it is pretty close to the bell-shaped, the peak being a bit plateaued here, but there are also a few outliers. We don't see much of the skews. Let's see, look at the normally distributed. Heart rate is minus 0.005, so very minimal skew. Body temperature is left skewed, it is 1.02 and calories 0.5, so body temperature and calories are well much skewed features. Yeah, so if you see in the body temperature, it is like so higher temperature values are much more in frequency of the counts here. Calories are lower, calorie values are much more, so the higher calorie values you'll find even lesser. And this is the calorie value which we'll have to predict. So this is how you can do univariate analysis, understanding outliers, distributions, their statistics, as in all the quantiles of individual features, numerical features basically. So also here you can understand which is the right skew. If the longer the right whisker is longer, quite a bit longer than the left one, then it means it is right skewed. Similarly, the scalaries, the body temperatures, left whisker is quite a bit longer. It means it's left skewed. There are a lot of outliers here as well in body temperatures. So now let's look at the bivariate analysis. First, we will try to understand correlations. So we plot correlation between each of the variables amongst each other. So if you see that the most dark colors are the highly correlating variables, wherein calorie is really highly correlated with duration, heart rate, body temperature. Body temperature is highly correlated with duration and heart rate. So these are kind of very directly proportional things. If you uh, work out for longer duration, higher chances are that your heart rate will increase and your body temperature will increase. So that justifies the higher correlation, positive correlation between these three variables and with the calories. So also weight and height are highly correlated. We'll have to see how they will turn up in case of doing the modeling. But yeah, that is also a good, simple, understandable trend that whoever are more in height, they would tend to be of higher weight. I'll just quickly turn on the lights. This is nice. Alright. So then let's take a look at for another way of doing bivariate analysis. We can take a look at scatter plots doing the numerical features. So here plotted different features, pair of features, calories against age, calories height. So basically, I try to see if there are any patterns in predicting calories with each of the uh, independent variable features. So you see that age, weight, and height have pretty uniform distribution against calories. There's no uh, uh, set pattern that you can find out here. But when you look at duration, heart rate, and body temperature, it is of an increasing nature. Linearly or not, we cannot predict right now, but it is. This is kind of a exponentially increasing nature. The body temperature, heart rate is increasing, but there's a naively, if we want to judge it, we can say that there should be a linear relationship between calories and these three: duration, heart rate, body temperature. But we'll see after finishing up the linear regression modeling part of this task that there's a particular thing called homoscedasticity, heteroscedasticity, due to which you will understand from these three figures, due to which our linear regression models are not working well enough rather. Okay, so data processing. First we map sex feature to make it Boolean variable. We make it to male 0 and female 1. So this is something that I think you should ignore right now. We'll talk about it later. We drop calories to make it the train data X. Y data is our calories. So these are some pre-processing steps, like scaling the features for each variable. For each feature in X, I'll subtract it with, I'll take the mean of X across X is 0. So basically across X is 0 means it will generate a mean value for each of the columns, and then we'll take the standard deviation of each of the columns. We'll perform this normalization step, so it will be centered around 0 as a mean. Okay, so this was about the exploratory data analysis. Now let's get into the modeling part of it. So here I have implemented a simple linear regression. Then I have implemented evaluation metrics that is being asked for. So if you look at this problem statement, they are asking for evaluation done with this metric, root mean square logarithmic error, which is different than RMSE, root mean squared error, where each of the errors basically, so not error, but each of the labels, true label or predicted label, are transformed with a logarithm and then subtracted to find the error, which are then taken a mean value out of and then squared. So this is the evaluation matrix. So I've implemented calculation of RMSLE. Then, so to start with, what I did is I implemented the simpler linear regression wherein we will just take one feature input and try to predict the calories. So you see that we have initialized weights, which is just one scalar because we are taking just one feature as input. Get params is basically if you want to look at the learned weights and biases. Predict is the method that we'll use when we are doing the prediction for the test data. So it is nothing but weight multiplied by x plus bias. Fit is our main method and evaluate is another main method. In fit, what I'm doing is I'm calculating the prediction for x, which is a forward pass. So basically, the idea is that linear regression can be approximated or can be optimized in different ways. Mathematically, there can be a solution which you can directly implement, which can be a bit tricky to understand the mathematical solution of getting, because the way of getting to the mathematical solution of the linear regression. But here what I have tried is I tried to solve it or solve for weights and biases using the gradient descent approach. So you see, I predicted for each example, I predicted the y-pred. Then I calculated loss. Loss is nothing but mean squared error. You take a mean of the square of the error. Error is y-pred minus y. Y-pred is what we are predicting here, and y is what we get in the input for fit method. Then we calculate gradients. Gradients is calculated with a formula that we can come to by mathematically finding derivative of loss with respect to weight of this particular formula. So this is loss. We need to find the gradient with respect to W and with respect to D. So we have to understand that y-pred is made out of W and D. So when you solve for dl by dW or dl by dB, L means loss, we will end up into these formulas. I'll try to see if I can make a quick derivation video from a notes doing the derivation of it and attach it to this as well. Then we use these gradients dWdB using the learning rate to update weights and biases, and we print the loss. We run it for a per set number of epochs. Epoch can be whatever you decide. These are the hyperparameters. Then we have also implemented evaluate method where you take in x and y. You predict on x. Then you have predicted x, predicted y's, and true y's. Then you take you basically take log of both. Log 1p is 1 plus this value and logarithm. So you avoid being the values being 0. We clip these void predicted values to 0 because we don't want anything to be less than 0. Otherwise, it will get to a non-number, not a number situation. Then we apply this formula. This is the same formula that you see in this Kaggle competition here. Just that the log spreads are calculated separately. And then when we print RMSLE. Now we break our data, train data into xtrain, xtest. We first scale them and we find make y. So we index them as per these. We have generated integers for breaking it into 80% of train data, 10% of validation development data or validation data, and then last 10% for test data. This is a naive baseline I tried to start with, which can be predicting everything as mean value of the trained set. So y test.mean. I make a y baseline as of length y test, and all the values will be the mean of the y's in y train. So RMSE baseline is nothing but the RMSE calculation for this, and RMSE baseline, the RSMLE baseline evaluation score would come from this. So this comes out to be 1.02. This is the naive method, the naive approach that we can see gives us RMSLE number of this much. So from here onwards, we move ahead and we initialize a simple regression model, simple linear regression model. So here, if you see, I have taken X as a single feature out of trained data frame, trained DF data frame, which is heart rate. Why did I choose heart rate is, if you go into the mutual information, there was a mutual information that I created. You can look at this code later, but body temperature was having quite a high mutual information interchange with calories feature. So that's why I chose to go with heart rate here. So we fit the model, simple model, X train and Y train for this 200 box and 0.1 learning rate. We see that we reached loss of 26. How many minutes have we done? Okay, sorry, I went for a break. So now, yeah, so as I was saying that simple linear regression, we fit it for 200 epochs, 0.1 learning rate, and I think within 100 also it's easily fitted, and we see with the evaluation. So how do we understand if the model is doing better or not? We evaluate it on test set for RMSLE. So these scores are 0.74 now, whereas the baseline score was 1.02. So we say that we have some improvement from our baseline numbers. To understand if we are doing our this class of models is doing correct thing or not, what I did is I took a linear regression class from sklearn and did the default training of it on the same data, X train and Y train. So we see that after predicting and evaluating it, we see that the RMSLE is exactly the same as what RMSLE we get from our custom model. And also I print the weights and biases of both the models, our custom model and sklearn. So you see that it's both coming out to be exactly same till 7-8 decimal places, and even the biases. So we can say that yeah, the implementation is correct. Now, next step was to make it a multivariate regression. In the simple regression, linear regression, I used just one variable. Now we must use more than one feature. So we take in the number of features as an initialization input for this class, and we initialize weights as per that. So weights would be a vector of random numbers of this length, of a number of features length, and otherwise most of the things would be same. Only output calculation would differ. This would be a matrix multiplication of x with self dot w. So each row will get multiplied. We'll do a dot multiplication with the entire w vector and then add the bias. The fit here would look very similar except the gradient calculation. So I think when I'm going to show the derivation of gradients of backpropagation, I'll show these both the cases, simple when I'm using one feature or multiple features. So we'll see this, how this np dot of x transpose and the error gives dw. So again, it's all the same thing, but here we choose in our train data two features, duration and heart rate. The split is similar, everything is more or less similar. I train this for learning rate 0.5 to 100 epochs. Within 100 only I reach to a loss that stopped minimizing that. So again, let's compare it with the sklearn model. So you see the weights and biases are more or less very similar, right? So here we have used two features, obviously. So we'll get two weights of length, vector of length 2, 43.88, 18.2 at 43.88, 18.2. So they are more or less same. np dot numpy all close is a function that can tell you to some approximation that the two numbers are, you can call them close or not. So with model, in this model, the evaluated score of our MSLE comes out to be 0.6282. So we can say that we have further improved by using two features as compared to the one feature. Now we tried with three features. Same thing, more or less. sklearn and our custom model weight parameters are coming out to be same. The evaluated score 0.51, so we have further improved from 0.62 after using three features. So we can say that there is a clear improvement in the evaluation score. Now some basic improvement in the implementation. So till now we have been doing stochastic gradient descent, wherein we were just we were calculating gradients over all of the train data once. We were calculating loss altogether. We were calculating output throughout the train data, calculating loss for entire data set, and then doing the gradient. So one entire data set, let's say it's a million data points. So all entire and 1 million data points are used to make a gradient update just once. So that's not a very good approach, because you can break it into many batches and we can make quicker, faster updates, more updates, and reach to the same point sooner. So that's what I do here. So we don't initialize W and P, because depending upon the size of the input, we'll need to initialize W. So also taking this as a class attribute doesn't sound very good, so I didn't do it. X dot shape gives you sample number of features. We initialize W and P. So we are breaking the data into many batches here. We are taking out a batch size parameter, for which we are choosing random indexes in the range of 0 to n samples, and generating batch size equal integer. So if batch size is 128, we are generating 128 integers in this range. Okay, so we make the X batch and Y batch out of these indexes by indexing. Then we do the same things, the calculation, the predictions, loss calculation, uh, computing the gradients, which I outsource to a helper function, compute gradients, and it's doing the same things that we were doing in the fit function earlier, updating the parameters and then printing the loss. Evaluation is the same. Now we train the custom linear regression for X train, Y train. I think it's with 3 variables. So now we are getting 0.5183. Still decent, still of the same order the evaluation score is. So here I inherited the previous class where we implemented mini batch and added L2 norm regression. So for L2 norm, you see how the loss is calculated is. Compute loss basically. Okay, so here loss calculation was outsourced to a new function, compute loss, and we are here modifying in the L2 regularization method class. We are modifying this compute loss function to add a penalty here. I think L2 penalty. So L2 penalty is nothing but scaling constant multiplied by the square of each weights summed all together. So there are 100, if there are 100 weights in the weight matrix or weight vector, they will all be squared, summed all together. You will get one number and you will multiply with a constant, this lambda. It will give you a L2 penalty. So in order to minimize this loss, the model should try to minimize RMSE and L2 penalty both. So to minimize both, it will try to minimize W, because W is what is seeing here. So it will try to keep W, individual values of W close to 0. It won't let them blast to higher values. And compute gradients would also change accordingly, because now you have two factors, two components to loss. So you'll have dW contribution coming from the RMSE and contribution coming from L2 penalty. Then we train this model. We see that our RMSL is nothing much better. So with this regularization, we'll one thing is what I feel is we'll see improvements, particularly when the model is complicated enough that it can actually accommodate regularization. Here we are not using so complicated models, so maybe it's not a big thing to worry about that we are regressing back in the RMSL scores after adding L2 regularization. Now a general model to use all the features. All the features are here in X-Train now. I make a custom linear regression instance, model instance, lambda value this 0.01. We train it, we find that RMSLE was reached to 0.6459. So still the RMSLE after using all the features are not improving any further. So here I just try to predict do predictions for the test set that we had to submit into the competition. And I noticed that the RMSLE, if I go to this, so here's the main catch of this problem statement. So if you go to the leaderboard and if you look at these scores, it is of order of 0.05841, and if you it takes time, but I scored down to at least 3,000-4,000 rank participants. It was still of the order of 0.0606 something, 07 something. So if you otherwise as compared to it, if you see the scores that we are getting, the best scores is I think maybe 0.5 something, right? So 0.51, that is of 10 magnitude order of 10 higher, 10 times higher than the scores that the people are the most of the competitors or teams are getting in the competition. So here the problem is, let's get back to the data analysis now. So here where we are doing bivariate analysis, if you see that these things, these patterns, we are trying to model them with linear regression, right? So we're drawing a linear line to define these. But there is a very basic assumption that linear regression model makes is that the relationship between predictor and dependent and independent variable is linear, and it is constant variance. The variance of the data shouldn't increase or decrease. So that is called that is denoted by the term homoscedasticity, skedasticity or heteroscedasticity. So let me heteroscedasticity. Let's see the Wikipedia page. So if you see this line here, this is quite a uniform width of the data points going up. So this is a linear relationship, but also the variance in the data is not changing. So this is called homoscedasticity, and this is the assumption, inherent assumption in linear regression. The data relationship between predictor and dependent variable, uh, predictor independent and dependent variables, is that it should look like this constant variance. Whereas in our data, it's not of constant variance. It has heteroscedasticity to it. So if you look at the plots here, all of these plots, they are of change in the variance. Here the variance is low, then the variance changes. Here also variance is changing. So fitting linear regression models to this problem particular is not beneficial. I did it for purpose of fitting for building a linear regression model from scratch and training it using the gradient descent. But for this particular problem statement is not suitable because of these two problems, homoscedasticity and heteroscedasticity. That's what I wanted to talk about in this video. Next videos, in the video I plan to implement from scratch on the video itself, how to build a tree, decision tree, random forest, gradient boosting decision trees, and the XGBoost trees. Maybe it will be a one video or two videos, I'm not sure, but I do try to do that. So we'll see how those are way better, and they can easily help us to get to the scores of this order 0.05, 0.06 easily with a scratch from scratch implementation, custom implementation that we'll do. Yeah. So thank you. Hope to see you again. Like if you like the video, if you appreciate the content. Thank you.